breathing new life into space exploration, a revolutionary oxygen generation method. In the vastness of space, one challenge stands out as critical, ensuring a steady supply of breathable air. While missions in low Earth orbit (LEO), like the International Space Station (ISS), can rely on regular resupply, deep space missions must find innovative ways to produce their own oxygen. Enter a groundbreaking study led by Álvaro Romero Calvo, an assistant professor at the Daniel Guggenheim School of Aerospace Engineering, Georgia Institute of Technology. The current method, electrolysis, has its limitations. It requires significant energy and struggles in microgravity. But here's where it gets controversial. An international team proposes a game changer, a method that harnesses the power of magnets for oxygen production. This alternative approach could revolutionize life support systems, making them lighter, simpler, and more sustainable. The team's research, published in Nature Chemistry, introduces a process called magnetic phase separation. By utilizing off-the-shelf permanent magnets and a passive phase separation system, they've demonstrated the potential to separate gas bubbles from electrodes in a microgravity environment without heavy, complex machinery. The experiments showed an impressive 240% increase in efficiency, thanks to magnetic forces improving gas bubble detachment. How does it work? The team developed two complementary approaches. The first guides gas bubbles toward collection points using water's response to magnets in microgravity. The second employs magnetohydrodynamic forces, a natural phenomenon arising from the interaction of magnetic fields and electric currents generated by electrolysis. This creates a spinning motion in the liquid, separating gas bubbles from water through convective effects. And this is the part most people miss. This magnetic process achieves the same phase separation as mechanical centrifuges used on the ISS, but without the need for mechanical rotation. As Katarina Brinkert, an honorary professor at the University of Warwick and director of ZARM, puts it, "We do not need centrifuges or any mechanical moving parts. It's a completely passive, low-maintenance system. The implications are huge. This research opens doors to developing simpler, more cost-effective, and sustainable life support systems for deep space missions." The team's 4-year journey, based on Romero Calvo's original idea, has led to a potential game-changer. As Dr. Shamika Saravanabhavan, a PhD researcher at the University of Warwick, highlights, "I'm proud to have contributed to advancing sustainable energy technologies beyond Earth applications." So, is this the future of oxygen generation in space? Could this method be the key to longer-duration crewed missions? The team aims to further validate their method by launching it into orbit, where it can operate in microgravity for extended periods. The potential is exciting, but what do you think? Is this a step towards a more sustainable future for space exploration? We'd love to hear your thoughts in the comments.